Hi, this is Mr. Champlin. We're starting off the year. Well, I guess this is the second video of over Chapter 1. This is going to be over graphing functions. Graphing functions. In terms of graphing, we're going to do a lot of graphing over the course of the year. Graphing is key not only to labs but also to the AP test. One of the standard problems within the AP test is to graph data and then determine an unknown value by using the graph. So think of all the different equations. You have to determine one of the variables in one of those equations. Data is typically given and labeled, then the students are expected to graph the data correctly to form a straight line. So you can't do a curved line, a square line, but a straight line. Students are expected to use the appropriate mathematical physics equation, so you have to choose the right one based on the data. So you have to know your concepts and know your relationships and know which one to choose, and complete an operation on the data that will provide a straight line. The data or calculated column of the data is then graphed on the appropriate axes, X or Y, using an appropriate scale. Be sure to label the axes and include units to earn full credit on the AP exam. The best fit line is graphed through the points. Then the slope is calculated and used to determine a known value. So I provided a couple examples here. Say you're given data over force and acceleration. In fact, the situation, if the data was given by measuring the acceleration on an object by applying various forces on the object, then we can relate it to the F equals ma equation. But again, they're not going to give you the equation, they're just going to give the data, and you have to make the connection what equation to use. Hopefully this is pretty familiar. This equation is pretty familiar with you. How do you determine which axis to graph on? Well, your independent variable always goes on the horizontal, and your dependent goes on the vertical axes. Okay, so if you think of a straight line on any graph, we have the equation y equals mx plus b, that is any line. So you want the x variable, or the independent variable, which is force, to be here, and you want your dependent to be over here. So what I have to do is rearrange this formula, and so I'm going to put ma over here equals f. I'm going to pull the mass over. And so basically that's the same relationship as that. It's just rearranged, but rearranged to the way it should be graphed. X variable independent, y variable dependent, and the slope should equal this coefficient. So you go ahead and figure out the slope of the graph. You can then in turn solve for the mass. Another example here is simple harmonic motion. Say in a situation you have a mass, or a variety of masses are attached to a spring and sent into harmonic motion. The mass is adjusted, meaning put in a different mass, 10 grams, 20 grams, 30 grams. And then each time the mass is adjusted, you measure the period, okay, for each mass. Then you're going to have to think, okay, what equation ties mass, period, and spring constant? I know that one, and you might remember from last year, as t period equals 2 pi m over k. So t being the period, 2 pi constant, m over k. Now we could do this one of two ways. First of all, you could graph the square root of m. Well, first of all, y equals mx plus b. Our independent variable is our x variable. In this case would be mass. We're adjusting mass, measuring period. So this is our independent, this is our dependent. So they're on the right side of the equation. I could factor out the k, graph square root of m versus t, and then I could get the slope to find k. The only thing I don't like about that is k is in a square root form in the denominator. So I'm going to, rather than doing that, I'm going to square both sides of this formula. So t squared and square this whole thing. That's clearing out the square. I end up with t squared equals 4 pi squared m over k. Alright, so now I'm going to separate my graphing variables. So m is graph. I'm going to pull out the k. And then I got my mass. So I'm going to graph t squared m. I have that data, or I can calculate t squared. And I'm going to get a slope, and the slope of that line should be 4 pi squared over k, and then I can solve for k that way. So those are two examples. Now we have a situation here where we're going to do a third example together. We have a toy car is placed in motion with an unknown mass. The kinetic energy of the car is measured at various velocities. So we have mass, we don't know, kinetic energy, and velocity. Mass, kinetic energy, velocity. Mass, kinetic energy, velocity. Well, I think that's the formula for kinetic energy, which we probably know from last year. KE equals 1/2 mv squared. All right. We need to manipulate the equation correctly. Well, let's go back to a straight line on a graph. Our y variable is our dependent variable. In this case, because we're adjusting the velocity, our y should be kinetic energy. So that's on the correct side of the equation. And our x variable is our velocity, but not, in this case, it would be velocity squared. So we are going to have to make a calculation. We are only given velocity. We have to actually square it. Therefore, the slope of the graph should be this term, 1/2 m. All right, so we have this new column. They usually do this on the AP test. They give you a new column to do any calculation you need. So we're going to call this new column velocity squared, and I'm going to put the units, meters per second squared. And I went ahead and did this square. So I'm squaring velocity, and I end up with these numbers. I'm doing this a little faster for the sake of time. So this is 11, and this is 18. This is 28, and this is 40. So that is the velocity squared. So the graph, just to review, just so we know what we're doing. Our goal is to solve for the mass. So our independent variable is our velocity. We're adjusting that, so that's going to be on our x-axis. Our dependent is on our y-axis. We should get a straight line. Our slope of that line should be equal to 1/2 mass. So we actually get to calculate the slope, solve it equal 1/2 mass, then in turn get the mass of this toy car that's this experiment is being done upon. Okay, got a big piece of graph paper. We want to fill the graph paper. We do not want a little graph. You want to fill the graph paper. How do you know what to do? Well, let's go back just for a second. What you do is you take your peak values for your y and your x, and you divide them by the number of squares or lines you have in your graph. So I've counted this already. I have 22x, 22y. So what I'll do up here, I'll do this little calculation. It was 40 was my peak value divided by 22. I've done this before. Comes out to be 1.8. I go a little bit above that because I'm going to keep it on the graph, not outside the graph. So I'm going to go up to 2. That's what I'm going to make each one of these subdivisions 2. Then do the same with my other variable. So it's 5 was my peak other value is over 22. Let's calculate that. 5 divided by 22. I get 0.23. So I'll go up on the next kind of whole number here. I'm going to go up to 0.25. And that's just to, you don't have to actually write that in your graph, but just to know so we can spread out this graph. So my velocity went up to 40, so I'm going to go up by 2's. So 2, 4, 6, 8, 10. 2, 4, 6, 8, 20. Whoa, let's erase some of that. Try that again. It's every 5, so 2, 4, 6, 8, 10, 1, 2, 3, 20. 30, 40. Now these are going up by quarters, 0.25. So 0.25, 0.5, 0.7, 1. So every 4, 2, 3, 4, 5. I'm going to graph the points. I remember from the chart, but the points were, let's see, 0.7, 5.3. So 5.3 is my velocity squared, 0.7, so somewhere right about there. 11, 1.5, 18, 2.2. Keeps on wanting for me to do that. I don't know why that. 28, 3.5, 28, 28, 3.5, and 40 is 5. Okay. You have a ruler, you have a straight edge. I cannot use that on this. So I'm going to draw the best fit line that I possibly can, but you'll do a much better job. Okay. Wow. All right. Let's do that one more time. I just cannot put that up there. Try this. That's a little better. Okay. I have already figured out the slope here because I'm not going to. What you normally do, just like you do in math class, you take 2 points, spread them out, hopefully where they cross an axis, and then change of y's. Or change of x's. Now I've already done this, so I'm not going to do this, but they want to actually see that on the AP exam. I figured out my slope ended up to be about 0.12. Now we know that the slope should be equal to half the mass. So 0.12 equals 1/2 m mass. Mass is 0.24. Sometimes they want a percent difference. That's experimental. Theoretical, it was supposed to be, the Matchbox car was supposed to be 0.25. So then to do a percent difference calculation, you do experimental minus theoretical all over theoretical, and all this times 100, change it into percent. So if you do this, you get 0.24 minus 0.25 divided by 0.25, absolute value times 100, ends up to be 4%. So that would be pretty good. That's anything less than 10% or so, it's good. All right, so that is how you do an example. You'll be doing some more on a worksheet.